So in today's class, we will discuss about some of the salient features or characteristics of kinetics of some of chemical reactions occurring with a different order. Okay, so we'll only concentrate on reactions which follow integral order. Okay, zeroth order reaction, first order reaction, second order reaction, and in general integral nth order reaction. Okay, so I will only discuss in detail about the mathematical derivation of kinetics of zeroth order reaction. A similar procedure can be used or followed for a first order, second order, and in general nth order reaction. Okay, so first let us concentrate on zero order reaction, or first let us define what is order of a reaction. What do you mean by order of a reaction? Order of the reaction is the molecularity of the slowest step occurring in the reaction. Remember, most of the reactions are not very simple. That is, they do not occur in a single step. When reactions do not occur in a single step, we have to consider the kinetics of each and every reaction, each and every step occurring in that reaction, and the overall rate of the reaction is decided by the rate of the slowest step, which is also called as the rate determining step, and the number of molecules of the reactant involved in that rate determining step, okay, is used to calculate what is called as order of the reaction. So what is a zero order reaction? A zero order reaction is a reaction in which the reaction or reaction rate does not depend on concentration terms. It does not depend on concentration terms of any of the reactants. So in this case, the rate of the reaction does not depend on the concentration of any of the original reactants that is involved in the reaction. So if I take a chemical reaction A giving product, okay, well, let us consider some simple reaction A giving product. So though this reaction suggests that the order of the reaction should be first order with respect to reactant A, okay, but this reaction is not very simple, that it is occurring in several steps, and out of those several steps, if I choose the slowest step, that is the rate determining step, which decides the overall rate, the rate determining step does not involve the original reactant A, it only involves some intermediates. So in such case, the slowest step or the rate determining step, since it does not depend on the original reactant, rate of the reaction does not depend on the concentration of the reactant. So generally, how do you write the rate of the reaction? The rate of the reaction is dx by dt is equal to, so generally rate of the reaction dx by dt is equal to rate constant A into concentration of A at time t to the power n, that is the order. In this case, it is equal to 0. Okay, rate of the reaction A to the power t to the power 0. So this is how we express the rate of the reaction. Remember, here I have written it as concentration of the reactant at time t, because time is very important factor in chemical kinetics. As time proceeds, as the reaction proceeds, the concentration of the reactant changes, in fact decreases. So at what time we are measuring rate is also very crucial, and that information should be given when writing this equation. So rate of the reaction at a time t is equal to rate constant into concentration of the reactant at a time t to the power 0. Why 0? Because it is a zero order reaction. So let us again rewrite this scheme here. I will rewrite this scheme, and let us try to understand in detail, okay, what is actually happening here. Okay, so at t is equal to 0, at t is equal to 0, that is the reaction has not yet started. Okay, let A moles per dm cube be the concentration of the reactant. So A is the initial concentration of the reactant before the commencement of the reaction, and since the reaction has not yet started, the concentration of the product is 0. At certain time t, okay, a certain amount of time t has passed, t maybe 1 minute, 5 minutes or 10 minutes, a certain time has passed, where we observe that out of a moles per dm cube, x moles per dm cube of a has reacted. And according to this reaction, you can see that for every 1 mole of A reacting, 1 mole of product is obtained. So for x moles of A reacting at a time t, x moles per dm cube of product B should be formed. So let us calculate the overall or the net concentration at time t. So what is the net concentration of reactant A remaining unreacted? What is the concentration of the reactant at time t? Remember, you have taken A moles per dm cube, out of which x moles per dm cube of A has reacted. So how much concentration of A is remaining unreacted? The answer is A minus x. So the concentration of the reactant remaining at a time t is A minus x, whereas the concentration of the product formed at a time t is x, because originally its concentration was 0. At time t, x moles per dm cube has formed, so the concentration of the product at time t is equal to x. Remember, A is a constant because it is the original fixed value, whereas x is a variable, it varies with respect to time. So this is the general kinetic scheme for a particular simple reaction. So let us try to substitute these things here. So dx by dt, that is rate of the reaction, dx by dt is equal to k into what is the concentration of A at a time t? Concentration of A at a time t is A minus x to the power 0. A minus x to the power 0. So therefore dx by dt is equal to k, because A minus x to the power 0 is 1. Okay, so dx by dt is equal to k. Rate of the reaction is equal to rate constant. Now this equation is in the differential form. Generally we express the rate of the reaction or the kinetics of a reaction in the integral form, because integral form is very easy to analyze and also very easy to express in graphical form. So let us rewrite this equation too and try to integrate this equation and obtain an integral form of this equation. So let us rearrange. Let us rearrange equation 2. Okay, so what I will do is I will take this term d into t to RHS. So we will get dx is equal to k into dt. Dx is equal to k into dt. Now let us integrate. So integration of dx is equal to, since k is a constant, okay, automatically it is removed from the integration constant. So k into integration of dt. What is integration of dx? X is equal to k. Integration of dt is d plus some integration constant c. So whenever you are integrating an equation, it is natural to see a integration constant c. And how to find out this value of c? Because until and unless you find out the value of c, we cannot obtain the specific form of the equation. So first let us find out what is the value of c. How to find out the value of c? For this we apply the initial condition method. Okay, a method that is generally used in integration for finding out the integration constant. So what is this initial condition method? We are applying the initial set of conditions on this equation. So what happens at when t is equal to 0? That condition we have to substitute here. So when t is equal to 0, that is reaction has not yet started. It means the concentration of the product should be equal to 0. ಯಾಕಂದ್ರೆ ರಿಯಾಕ್ಷನ್ ಸ್ಟಾರ್ಟ್ ಆಗಿಲ್ಲ ಅಂದರೆ ಯಾವುದೇ ಪ್ರಾಡಕ್ಟ್ ಫಾರ್ಮ್ ಆಗಿಲ್ಲ. ಸೊ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಪ್ರಾಡಕ್ಟ್ ಎಟ್ t is equal to 0 should be equal to 0. So x should be equal to 0. Concentration of product is equal to 0. Now let us substitute this initial condition in equation 3, because this equation 3 holds good for all values of x at time, and therefore it should also hold good for this condition also. T is equal to 0, x is equal to 0. So let us substitute. Therefore 0 is equal to k into 0 plus c, which shows that integration constant c is equal to 0. So in this case integration constant is 0. So the equation therefore we are supposed to deal with is x is equal to k into t, or if I rearrange this equation, k is equal to x divided by t. So these are the governing equations for a zero order reaction. X, the concentration of the product formed or the reactant consumed, is equal to rate constant into time t, or this is the well known form. The rate constant of a zeroth order reaction is equal to x divided by time t, applicable for a zeroth order reaction. Now let us find out what is the unit of rate constant k. Okay, since according to this equation rate constant is equal to a concentration term divided by time. So what is the unit of concentration? Mole per dm cube, and time, suppose if it is expressed in minute, so unit of k is mole per dm cube per minute, or mole per dm cube per second. So the unit of a zeroth order rate constant is mole per dm cube per minute. Okay, so unit of k is mole per dm cube per minute, and this is only for a zeroth order reaction. This is applicable for a zeroth order reaction. Remember, as I told you in the previous class, the unit of rate constant varies, okay, as the order of the reaction varies. Now let us try to understand the mathematical or the graphical implication of this equation. Look at this equation. This is a linear equation of the form y is equal to mx plus c, where c is equal to 0. So this equation is of the form y is equal to mx. So if I plot, okay, the values of y along y axis and x along x axis, then y versus x should be a straight line passing through origin, because it is a straight line. So suppose if I measure experimentally the values of x at a different time t, that is at different time t, say for example 5th minute, 10th minute, 15th minute, so on, I am measuring what is the concentration of the product formed, that is x at a different time t, and plot a graph of these values. It should be a straight line passing through origin, because this equation is a straight line equation with c is equal to 0. So you get a straight line passing through origin. And what should be the slope of this straight line? According to equation 4, the slope of this equation is of the form y is equal to m into x. Okay, where y is x, x is t, m is the slope, therefore slope is nothing but rate constant k. So suppose you know that a particular reaction is zeroth order and you are interested in calculating the rate constant of the reaction. This is one of the method for finding out the rate constant, provided you know it is a zeroth order reaction. Plot x versus t, you will obtain a straight line passing through origin. Find out the slope of that graph or straight line. It is nothing but the rate constant. On the other hand, if you are carrying out some new reaction and you are interested in knowing whether it is a zeroth order reaction, how can you find out whether it is zeroth order reaction or not? Calculate x at different time t, okay, or measure the values of x at different time t. Plot x versus t. If you get this straight line with this characteristic straight line passing through origin, it means it is a zeroth order reaction. Alternatively, you can have another plot. Okay, you can have another plot. Let me rewrite this equation for again here. X is equal to k into t. Okay, I will multiply by -1 on both the sides, and I will add the initial concentration term A on both the sides. I'm adding, so A minus X is equal to A minus KT, or I will write it as A minus X is equal to minus K into T plus A. I've just rearranged the RHS. So this is nothing but equation 4 written in a slightly different form. Now we will look at this equation 5, which is also an equation for a zeroth order reaction. So here X is a variable, K is a constant, time is a variable, initial concentration A is a constant. So this equation is also of the form y is equal to mx plus c. So instead of plotting x versus t, you can now plot, okay, you can now plot A minus x, that is your new y, versus t, A minus x versus t. Okay, and if the reaction is zeroth order reaction, it should follow this linear equation. In that case, a plot of A minus x versus t should be a straight line. So see here, y is equal to mx plus c. Here c is not equal to 0. So though you get a straight line, that straight line will not pass through origin. It will have a definite intercept. And since the slope is negative here, you are supposed to get a straight line with negative slope. So the characteristic of equation 5 is it is a straight line with negative slope and with a definite intercept. And what is the intercept according to equation 5? For this graph, the intercept is the initial concentration A. And what is the slope of this line? The magnitude of slope is K. Okay, so the magnitude of slope is nothing but the magnitude of rate constant K. So either you can plot a graph of x versus t, or you can plot a graph of A minus x versus t in order to obtain the or verify the rate constant, in order to verify whether the reaction is zeroth order. And if you get this characteristic graph, you can find out what is the rate constant of the reaction. So this is the salient feature of a zeroth order reaction. I will give one example for a reaction following zeroth order reaction. It is decomposition of nitrous oxide on platinum. Okay, so this is one of the reaction which follows zeroth order kinetics. Or you can also have decomposition of ammonia on the surface of tungsten or molybdenum. So ammonia on the surface of tungsten or molybdenum. Okay, so it undergoes decomposition following a zeroth order kinetics that we have discussed here. Okay, so this is about a zeroth order reaction. Now let us discuss about a first order reaction. So what do you mean by a first order reaction? A first order reaction, okay, depends on the rate of a first order reaction depends on the concentration of one reactant. So the reaction rate depends on concentration term of only one reactant. So rate of the reaction now depends on the concentration term of only one reactant. So though the original reaction may contain 2 or 3 reactants, the rate determining step, that is the slowest step, okay, in that slowest step only one original reactant participates. Therefore rate depends only on concentration of one reactant. The example for such reaction is a well-known example of acid catalyzed hydrolysis of an ester. So for example, if I take methyl acetate, CH3COCH3, okay, in presence of few drops of HCl or sulfuric acid, undergoes hydrolysis to give the respective acid and alcohol, respective acid and alcohol. Okay, so how many molecules of the reactants are involved? 2 molecules are involved. So the molecularity of this reaction is 2, but the order of the reaction is actually 1. Here rate actually is equal to rate constant into concentration of ester to the power 1. So rate of the reaction depends only on the concentration of the ester and not on the concentration of the other reactant, water. So such reactions are called as pseudo first order reaction or pseudo unimolecular reaction, pseudo first order reaction. Okay, why? Because though the reaction suggests that it is of second order, or though the molecularity of this reaction is 2, the order of the reaction is just 1. So such reactions are called as pseudo first order reaction. Okay, you can derive the expression for rate constant by using the same procedure that I had demonstrated for zeroth order reaction. Write the reaction scheme, okay, then substitute it in the rate equation, rearrange and integrate, find out the integration constant, you will get the value of k. Okay, I will not do all those things because they are not in your syllabus, so I will directly give what is the expression for k. So for a first order reaction, rate constant k is equal to 2.303 divided by t into log of a by a minus x. So this is the expression for rate constant of a first order reaction. T is time, A is the initial concentration of the reactant, a minus x is the concentration of the reactant at the time t, or you can say x is the concentration of the product at the time t, or you can rearrange this equation and write, okay, log of a by a minus x is equal to k divided by 2.303 into t. So equation 2 is nothing but the rearranged form of equation 1, or you can further write it as log of a minus x. Okay, this is also rearrangement. Log of a minus x is equal to minus k divided by 2.03 into t plus log a. Okay, you try to rearrange equation 2 by using the logarithmic rule. Log of a by b is log a minus log b, and make some rearrangement. You will definitely obtain this equation. 3 log a minus x is equal to minus k divided by 2.03 into t plus log a. So any one of this equation, okay, you can use to represent the kinetics of a first order reaction. Okay, so before going into the graphical aspect of this reaction, let us first concentrate on this equation 1 and try to find out what is the unit of rate constant k. So let us concentrate on RHS. 2.303 is a unitless quantity. In denominator you have time, and here you have log of concentration term divided by concentration term. So the unit of the numerator cancels with the unit of the denominator, so this is a unitless quantity. So the unit of rate constant is nothing but the inverse or the reciprocal of the unit of time. So unit of the first order rate constant is just time inverse, that is minute inverse or second inverse. What about a zeroth order reaction? The unit of rate constant of a zeroth order reaction is mole per dm cube per second or mole per dm cube per minute. But for a first order reaction, it is per minute or per second. So as I already stated in my previous class, the unit of rate constant changes as the order of the reaction changes. Now the question is how to verify whether a given reaction follows first order reaction, or you already know that it is a first order reaction. How can you find out the rate constant of the reaction? Again, one of the method for determining the order of the reaction is graphical method. Okay, there are different methods which we'll discuss in detail in the future classes. It is there in your syllabus. So here I'm just concentrating on some of the features, salient characteristics of a first order reaction. So how to plot a graph? What is the characteristic graph for a first order reaction? Now for that, let us concentrate on equation 2 and equation 3. Equation 2, okay, let us try to find out which are variables and which are constants here. A is a constant, but x is a variable. It varies with respect to time. So overall a by a minus x is a variable. Here k is a constant, 2.03 is also a constant, time is a variable. So equation 2 is of the form y is equal to mx plus c, but c is equal to 0. So equation 2 represents a straight line passing through origin. So you can choose equation 2 to plot a graph for a first order reaction, because it represents a straight line with passing through origin. So what we do is, at a different interval of time, find out either the value of x and then calculate a minus x, or directly find out experimentally what is the value of a minus x and then plot a graph of log of a by a minus x versus t. And if the reaction is a first order reaction, it should be a straight line passing through origin, and the slope of this reaction is equal to k divided by 2.303, from which you can calculate k is equal to 3.303 into slope of the reaction. Alternatively, I can use equation 3. Here a minus x is a variable, k divided by 2.303 is a constant, into time t is a variable, plus log a is again a constant, because a remains constant because it is initial concentration. So this equation is of the form y is equal to m into x plus c. So it represents a straight line with a definite intercept or non-zero intercept. So alternatively, instead of plotting log of a by a minus x, if I only take log of a minus x versus t, what should happen? Again, since the slope is negative, I will get a straight line, but with the negative slope and non-zero intercept. So I will get a straight line with a negative slope and non-zero intercept. What is the intercept of this straight line? Intercept is log a. And what is the magnitude of slope of this straight line? It is again k divided by 2.303, which implies k is equal to 2.303 into slope. Remember, for a zeroth order reaction, the y-axis changes. Either you plot x versus t, or you plot a minus x versus t. But for a first order reaction, the y-axis terms are different. So each reaction, whether it is a zeroth order reaction or a first order reaction, you have a characteristic graph, and by using that characteristic graph, first you can ensure that is whether it is a zeroth order or a first order reaction, and after ensuring that it is a zeroth order or a first order reaction, from the graph you can find out rate constant of a reaction. So this is about a first order reaction. Now let us concentrate on a second order reaction. What do you mean by second order reaction? Here the rate of the reaction depends on two concentration terms of reactants. Rate of the reaction depends on two concentration terms of the reactants. Okay, let me give a simple reaction. Suppose if I have 2A plus B giving product. Okay, so reaction of molecularity is equal to 3 because there are two molecules of A and one molecules of B. But the rate of the reaction depends only on two terms of concentration. And that you know, the slowest step or the rate determining step consists of only two original reactant concentrations or terms. Which two? Whether it is two molecules of A or one molecule of A and one molecule of B. Okay, so the rate of the reaction may be dx by dt is equal to K into concentration of A into concentration of B. This scheme also scheme represents a second order reaction because it is depending on one concentration of term of A and one concentration of term of B. So it is a second order reaction, or we may not know the rate of the reaction may be dx by dt is equal to K into A square. Okay, so there are two cases in a second order reaction. The rate of the reaction may depend on two concentration terms of same reactant or one concentration term of each reactant. So for a second order reaction you have two types of cases. If the initial concentration of the reactants are same and if the initial concentration of reactants are different. Okay, so if the initial concentration of reactants are same, then this equation and this equation gives same outcome. Okay, yakandre if concentration of A is equal to concentration of B, initial concentrations, this term and this term are one and the same. But if the initial concentration of the reactants are different, that is concentration of A is not equal to concentration of B, then these two terms yield different results. So in second order reaction we have to consider two types of cases: if the initial concentration of the reactants are same and if the initial concentrations of the reactants are different. So first let us concentrate on what happens if the initial concentration of the reactants are same. So if the initial concentration of the reactants are same, that is concentration of A is equal to concentration of B is equal to A. In such case, okay, if we follow all the mathematical equations, okay, the final expression that we get is rate constant K is equal to one by T into X divided by A into A minus X. Okay, so the rate constant of a second order reaction will be equal to 1 by time into X, that is the concentration of product formed at time T, divided by concentration of A, initial concentration of the reactant, into A minus X, that is the initial concentration of the concentration of the reactant at a time T. So this is an expression obeyed by a second order reaction. You can rearrange equation 1 in different form. Either you can write it as X divided by A into A minus X is equal to K into T. X divided by A into A minus X is equal to K into T. This is one form of writing equation 1. You can further rearrange, okay, and write it as X divided by A minus X is equal to A into K into T. Okay, A into K into T. There is one more form of writing this equation. It is 1 divided by A minus X is equal to 1 divided by A plus K into T. into T plus 1 divided by A. 1 divided by A minus X is equal to K into T plus 1 divided by A. So equation 1 to 4 are the different forms of writing the second order rate equation in the integrated form. Now let us first find out what is the unit of K. So the unit of K, okay, so here you have in the denominator concentration term, time. Here you have concentration divided by concentration into concentration. So unit of K is 1 by unit of time, that is 1 divided by minute, into concentration X mole per dm cube divided by A into A minus X. So mole per dm cube into mole per dm cube. So mole per dm cube gets cancelled. So the unit of K, if I take everything to denominator, it becomes mole to the power minus 1 dm cube minute inverse, or you can write it as mole per dm cube whole to the power minus 1 minute inverse per mole dm cube per minute, or mole per dm cube whole inverse per minute. So this is the unit of the rate constant of a second order reaction. Right, now let us try to find out what are the different possible ways in which you can graphically represent a zeroth order reaction.